Hi, folks, and welcome to week 2. Share my screen. We are going to cover beaches of the world today. So there's lots of different physical attributes of the beach. We're going to go over those first. So, really, what is a beach, right? We think of the beach as sand, waves, water, sun. But what we want to look over is going to be, as a biologist, which is what I do, is really looking at habitat for all the critters that live there. So maybe you've seen crabs, little sand crabs or big crabs or fish. We also have tiny, tiny organisms or critters that live down in the sand, that live in the water. You can only see with a microscope. Then as a geologist, like Dr. Patch, or maybe an engineer that you see out moving sand around, they define beaches more about grain size and sand, anywhere from a tiny grain to a big boulder, right, that forms waves along the coastline. So anything from the dunes or the vegetations, the little plants, that go all the way to an offshore depth where you don't see sand anymore, or it's really rarely there. So if anybody has been scuba diving, you get out a ways, you can't quite see the sand anymore. And then for the casual beachgoer, like most of us, it's just towel space for fun, right? Makes it a lot nicer. So how do you make a beach? This is a picture of Manhattan Beach in California. It's very groomed. So to start with, you need a supply of sand or gravel, which we were going to call sediment. You have the energy of the waves. Yes, that is part of beach making. You have a setting where the sand can accumulate. So if you've ever been to the beach and sat down, you know the sand can accumulate in your shorts or in your bathing suit. And you kind of think of the beach as that supply spot where things settle in. And you have to have the sea or even a lake. Lakes help with sand too. And with all of those together, you form what's called a dynamic equilibrium. And when any of that changes, the beach changes. So if you have less wave energy or you don't have any sand, that's when your beaches change, which I'm sure you might have noticed, or you're going to notice now with this class, how our beaches are really changing. So all the beach sediment, meaning the sand, can be different sizes, shapes, colors. So along the California beach, our sands come from the mountains, really, and it comes all the way down through the rivers out to the sea, one way or the other. In a place like Hawaii, the sand is really fish poop. Yep, it's fish poop. They eat the coral and poop it out, and it gets washed up onto the shore, or it's volcanic rock broken down to made into different sizes of sand. So we have green beaches in Hawaii, which is a different kind of rock. And then we have black beaches, black sand beaches, which is volcanic rock sharpened down. And so each of these differences show the diversity of beaches, right? And so here's a really pretty picture of the green sand beach on the South Point in Hawaii. Olivine is a green rock. We have olivine in California too, but there's a ton of olivine here. And it's really, really beautiful if you ever get a chance to see it. We also have red sand beaches, and this is in Maui where I actually live. And it's because there's a ton of iron in the rock. So when you get really close, you can see all the different really cool colors of the beach, and it's beautiful. It makes the water really, really pretty. Then we have Harbor Island, or if you've ever seen a picture of the Bahamas, they have super white sand to the point where it's pink. The red coral in the water actually is pooped out by the fish, and it settles along the coastline. So you have this pink sand. It's very, very pretty. Then here's our black sand beach. So this is the one on Hawaii, the Big Island. We also have one on Maui, and it's where the lava has flown down into the ocean, and it's called basalt. When it finally reaches the surface, it forms this really beautiful black beach. This beach is very hot. There's a cove on the island of Hawaii on the south side where it's hot, but that's also where the dolphins rest in the water. So you go to the black sand beach, it's beautiful there, and then the spinner dolphins relax and hang out in that little cove if you ever get a chance to go. Hyams Beach is in Australia. This is super white. It is the whitest sand in the world. I've actually never seen this, but it's on my bucket list. It's a beautiful, beautiful place. And those of you in the group that have Australia for your beach, maybe can look into this. Pfeiffer Beach is in California. And if any of you have been up towards Big Sur where condors are, this comes down, it has all these really cool colors because there's manganese garnet in the sand. So when the rain washes it down from the river up above, it comes down into the beach and makes all these really pretty colors. So there is, of course, one old guy who created the size class for sediments. It's called his last name was Wentworth. So, you know, that's the deal when you're a scientist. If you find something first, they name it after you. So there's a lot of old white dudes. That's just how it is for right now. We're working on the rest of it. Very coarse sand is 1 to 2 millimeters. So as a concept, the width of your pinky nail across from one side to the other is usually about 5 millimeters. Okay, maybe a little bit bigger. And so very coarse sand is 1 to 2, and so on. It goes down. Very fine sand. The is called microns. You can only see that with a microscope. So where does the sand come from? California, it comes from the rivers. Most of our sand comes from the rivers. It all depends on where it came from, depending on what it looks like. So if you go to a different beach, if you go to a beach closer to a large river mouth that's maybe not dammed up, you'll notice that possibly the sand is larger. If you are at a beach that's farther away from a river mouth, it's usually smaller. Depending on the kinds of rocks that are along the mountains there, that will be the color and the shape of the sand. You know, rocks get broken down. If you notice, even a rock that you might have picked up somewhere and you rub on it for a long time, eventually it gets smooth. It's the same kind of concept with the waves and the sand. Oh, the white sand on the beaches for all the tropical areas come from offshore reefs. That's the nice way of saying the fish poops. Sea cliffs also provide the beach material. So I know, let's see, where are cliffs? If you're driving up towards Santa Barbara, we have the cliffs on the right-hand side that have many times eroded away. If you go south towards San Diego, that's an issue. And then going north towards Santa Barbara and Isla Vista, you can see it. I'm trying to think of the areas close to see the cliffs that erode. And then if you ever get up to go out to Santa Rosa Island on the far west side, we have natural beach cliffs. You can see it's really cool. Gravel beaches are a lot of gravelly streams. So up in Oregon, there's a ton of gravel that comes down the streams. And so that sand can be a lot more coarse right next to the river mouth. Or if you are in a tropical area where you have coral fragments and different shells of critters. So this is our Santa Barbara. This is what the bluffs look like. So it's eroding down because of the wave action, and people built right here, and now things are falling into the ocean. This is the Santa Clara River mouth, which is just south of Ventura Harbor. And as you can see, the beach is fully closed here. So what happens is when the beach closes it all in, it doesn't allow all that water to come through. Usually it takes a winter high tide and solid waves to break through this river mouth. And then we have eroded reefs, white sandy beaches, which is really more something that you see in warmer waters where hard coral is. So we do need waves to move that sand around and shape the different things to be smaller, because everything starts as a big rock generally on our beaches in California. And after wind and waves and sun and tumbling around, it gets smaller and smaller and changes position. And that's how you get your beaches. So there's no beach that is the same as another beach, and it always changes because it's a dynamic ecosystem, or a dynamic ecology rather. If you'll notice, in the summer, beaches are very different than the winter. Even after or before a storm, you'll notice huge differences. A hot day, cold day, you'll start to see things when you go out to the beach. So when do you get a beach? It has to trap the sand, right? Remember how I talked about when you sit down on the sand and you get it in your shorts? Same kind of concept, right? If it's just a big long coastline and there's no bluffs, there's no river, or there's huge rock cliffs, they usually don't have beaches. But it's when there's a little pocket, right? A little catch area like this beach down here on the left that you can start to get sand accumulated, and it gives you a beach. Also, it really depends on the elevation of the sea level. So, you know, at low tide, obviously there's a lot more beach, and same kinds of concept as we are losing a lot of our beaches because sea level is rising. And so where there were beaches before, we don't have them. Normally, if there is not a large buildup of houses or buildings, the beach will just kind of move itself back. So the mountains or the hills will erode and create beach as it backs up. And we'll talk about this a little bit more and why it doesn't happen quite as much. So in order to make a beach, it depends on the shape and the location. These are the three things. We need sand supply, changes in sea level, and waves, something to remember. So here's another old guy that decided that these are the different two types of beaches. We have a primary beach. That's all the shape that comes from the land processes. So that means anything coming down from above. Alluvial fans. So where campus is, and all of the Oxnard Plain is an alluvial fan. So many millennia ago, a volcano erupted and spread out all of this really rich in mineral rock and sand, and it's spread out into what we call the Oxnard Plains now, and that's why there's so much agriculture there. So that's what an alluvial fan is. Lava coasts are something that you think of in Hawaii, where active lava is pouring into the ocean and becoming a bigger and bigger island. The fjords are up in the colder area, where you're getting icebergs and whatnot. And then the river deltas, where you have really large rivers that go along the big coastline. And then secondary beaches are formed by marine processes, like waves that straighten out the coast, barrier islands, like we have on the East Coast, and then the coral reefs, which created a separate kind of coastline. So some primary examples are a drowned glacial valley or a drowned river valley. That's what happens when there's erosion. So you might have seen, like on TV, how some of the glaciers are melting and falling off. And so that's what we're talking about. And a drowned river valley is maybe the recent floods that we've seen in the South, where it's a low-lying area and the rivers rise and drown that valley. And unfortunately, a lot of people get hurt that way. Deposition examples, like sand dunes. If you've ever noticed how the little fences are put up along the beach and the sand kind of collects there, that's a man-made way of doing it. But we also have sand dunes with flowers and plants, and they do that automatically, collect the sand. Glacial moraine is those deposits left by those glaciers. And then we have the deltaic river deposition at the river mouth, similar to what I showed you with the Ventura River mouth. And then the volcanic examples. Lava is still flowing right into the sea on Hawaii Island. And then old craters that are flooded by seawater. Almost positive there's one like in Colorado somewhere, I'll think of it. And then we have the tectonic examples. So different faults. So coastal faults are filled with seawater, and that's something underneath that you don't see. But we'll also talk about that. So this is a fjord or a glacial coast that's been drowned by sea level rise, happened over millennia. This is Hawaii. This is Hawaii Island. No, this is Maui, because that's Honolulu Bay, formed by volcanic activity. Then we have the new volcanic coast. So this is Hawaii Island, and the volcano is behind the clouds, and you can see the new coastline forming. Molokai is an older island. It's an inactive volcano, but you can see that the Coastline has changed and caught on that bottom part. There's huge cliffs, but they've all been grown over because it's much older. And then in Taiwan, this is a fault line immersion where two faults come together and you see the rocks go straight up in the air. Obviously, this happened millennia ago, but you can see this is how the coastline is formed. And then we have the Mississippi River Delta. So this is an aerial photo that you see all the sand and the stuff coming out of the Mississippi River, and it goes into the ocean, and then it forms a coastline when we have waves and hurricanes. Chesapeake Bay is a drowned river valley. So that means it's very low-lying valley covered up by water. And then we have our coastal cliffs here in California. 13% of that is these really high, steep cliffs along the coastal mountains. So it's very, very pretty to see. 28% of California is lower land. So we have estuaries, beach dunes, lagoons, and bays. 310 miles of that coast is lowlands. You don't see it as much anymore because it took a long time to protect these areas. Then we have the secondary coasts, which I talked about. Erosion with waves, deposition of sediments, and then the alterations by the little plants or animals, things that happen. Our secondary coast examples are regular cliffs or irregular cliffs. When the deposition is the barrier coast, so barrier islands or sand spits off the island of, what's the one? North of Santa Rosa. That sand spit changes about every 3 years. Mud flats and salt marshes is something you can see just north of Point Mugu. Point Mugu on Ormond Beach is a huge mud flat that you can see. And then things that are built by critters or marine organisms are coral reefs, mangroves, and marsh grass. So when the waves erode the coastline, which is what we see here a lot in California, is the waves come up and hit the exposed beach and break through those sea cliffs. Sometimes it breaks through and creates an arch or a blowhole, which we see in Hawaii a lot. But this is how the waves come up and smack into the beach and erode the coastline. This is a really good example. As you can see, the rocks have been slowly worn down, smashed into the eroded cliff and leaving more sand towards the bottom. Coastal cliffs, this is something that you can see where the waves obviously come up and are eroding the baseline, making really cool caves, but also slowly eroding away to collect sand at the base. And then this is also another example in Australia where this coastline, a millennia ago probably looked like the cliffs that we just saw, but has been eroded away by waves over time. In France, this is really cool. It's beautiful, this really pretty arch off of Normandy. This is another wave eroded by coastline. The arch at Anacapa also looks similar to this. In Portugal, it's another wave eroded coastline. So marine deposition is when there's a current that heads down, say north to south, and it moves along with its sand and it gets collected in places like the bays where we call it like a sand spit or in a lagoon, and little bars start to form because the sand maybe settles in there. A lot of times with a barrier island that creates some sand catch, or tombolo where there's a little tiny sea island out to shore, but underneath there's maybe some leftover rocks that have been eroded that catches that sand. There is a slight margin, or what we call a passive margin, on a barrier island. So the barrier island of Maryland on the East Coast creates this catch for sand. However, humans have altered it because we've put the shoreline a little bit different from building things out for passages for boats and whatnot. So this can be altered, but generally, it just depends on, if it's human activity alteration. As you can see at the top, this is from 1849, and humans haven't messed with this one too much. There's just been some change based on wave action and whatnot. but the bottom island has been definitely purposefully changed, making it closer to protect Maryland, to keep the bay probably for fishing, and to let those boats out in that inlet right there for Ocean City. So you can see all the human changes, right? What do you notice the most? There's tons of houses and bays and man-made sand catches so that we have that beach there. Mangroves are amazing. Mangroves are a warmer climate plant. There's a bunch of different types of mangroves. They create their own little ecosystem. Little fish and crabs and whatnot live underneath mangroves. They trap sediment. They filter out the crud from the water before it goes out into the ocean. Mangroves are really fun and cool. If you ever get somewhere warm, check them out. This is what they look like. It's like an underwater jungle. It's nuts. It's all these crazy roots. Those are all mangrove roots. And underneath, you'll see tons of fish and cool stuff. All right, so then we have this other classification based on wave energy. So again, another old man. He had a very long career, and he created classifications of wave energy based on different heights, right? So low energy beach is 1 foot, or, I don't know, knee high. Moderate is about 2 feet, a little bit higher, that like thigh high, and high energy is, waist high waves. He developed this classification for Mexican and US shores, but didn't translate. It didn't really go around the globe very well, right? So it's older, it's fine, and we've moved on from then. But the important thing for you to remember is wave energy and the 3 classes. In the 80s, Don Wright and Andy Short figured out that there was 2 endpoints. This is actually really important: the dissipative beach and a reflective beach. They included not only the wave height, but the beach sediment, okay, and the way the beach changes. So a reflective beach is really steep. So let me think of a really steep beach. Somewhere in Malibu, along those bluffs. Usually the greens, the sand is really coarse. There's no bars offshore. The waves break right on the beach. And it's a wide beach, but not really wet. So the water doesn't usually come all the way up. Where a dissipative beach is like a wide surf zone. So it's pretty flat. So say something like Zuma Beach in Malibu or Solomar Beach in Ventura is going to be more of a dissipative beach. There's a little bar offshore where a lot of critters hang out and do stuff, and it's fun for recreation. Or like a big beach like Santa Monica would be another dissipative beach. So we also have the plate tectonic classification. So here in the red, you can see the different plates that go over the mantle of the rocky inner layer of the core of the Earth. And when those plates grind together, things come up from them, and that's how we get a lot of really interesting rocks and cool shorelines. So this was proposed by Doug Inman in 1971. So the leading edge is when the plate that has the continent collides into an oceanic plate. Those rocks are deformed and lifted to form the coastal mountain ranges. So things like the Pacific Mountain Range, the Japan Islands, the Philippines, the Andes Mountains. This is the deformation and the volcanic activity, as well as subduction zone. So this is a lot of geology, but just remember the leading edge and trailing edge and how that the rocks come up from the oceanic plate. Sea cliffs, little pocket beaches are formed this way. This is all up and down California, Chile, and Peru. The passive margin is more near the spreading center of the plates. So on the opposite side of the leading edge. So you think about Europe and more about North America, the Atlantic Ocean basin. Those continents spread out, and so they shed huge quantities of sand. Like basically, if you break apart a really crusty croissant or something, and all the little pieces fall in, think of that as like 2 big continents that break apart, and all that sand goes in, and it creates a huge wedge, and that's what we call the Atlantic basin or the coastal plain. And there's not a lot of big waves. If you've ever been to the East Coast, not a lot of waves. And then they have really long beaches along the shore. So an active margin we have here on the West Coast, as Palos Verdes. As you can see, tons of wave action. There was lots of volcanic activity here, lots of geologic change. And then, this is how you get this really crazy coastline. A passive margin along the East Coast. It's just long and flat and not a lot of waves. You have Miami here. It's warm, there's low level, lots of water, but not lots of big waves. You can watch this movie called The River of Sand on your own time. There's a link in both the lecture and in your module. And that's it for today. If you have any questions, you can rewatch the lecture. You can always shoot me an email, and I look forward to reading your discussions.